What if you could witness the very first light in the universe? Picture a time so ancient, so unimaginably distant, that the cosmos was nothing but an endless sea of darkness, until something extraordinary happened. This was the cosmic dawn era, the moment when the first stars flickered to life, tearing through the void and igniting the universe as we know it. But here's the thing, despite everything we've learned, this era remains one of the greatest enigmas in all of science. We're talking about mysteries so profound they rewrite the rules of physics, challenge our deepest cosmic theories, and leave even the brightest astronomers scratching their heads. Think about that for a second. These weren't just any stars. They were the pioneers, the cosmic trailblazers that shaped everything that came after. Yet we still don't fully understand how they formed, why they burned so fiercely, or what secrets they took with them when they vanished. And that's just the beginning. From ghostly signals buried in the static of space to galaxies that shouldn't exist this early in time, the cosmic dawn era is packed with puzzles that defy explanation. It's like uncovering pages from a story written 13 billion years ago, only to realize half the words are missing. That's exactly what we're diving into today. Over the course of this journey, we'll unravel 25 of the most baffling, mind-bending mysteries from this primordial chapter of the universe. Some will make you question reality, others might keep you up at night, but one thing's for certain: by the end, you'll see the cosmos in a whole new light. So are you ready to step into the unknown, to peel back the layers of time and explore the echoes of the very first dawn? Let's begin. At the very edge of cosmic history, where time itself seems to blur into darkness, the universe was an entirely different place. No galaxies, no planets, just vast clouds of hydrogen and helium drifting in the void. Then, out of that emptiness, the impossible happened. The first stars ignited. These weren't just stars, they were titans, behemoths hundreds of times more massive than our sun, blazing with such intensity that they lit up the cosmos for the very first time. Scientists call them population 3 stars, and yet, here's the strangest part: we've never actually seen one. What makes these ancient giants so elusive? For starters, they lived fast and died young, burning through their fuel in mere millions of years before exploding in violent supernova. But even their deaths were extraordinary, seeding the universe with heavier elements that would eventually form planets, life, and even us. The problem: they existed so long ago, their light has stretched into near invisibility over billions of years, slipping through the grasp of even our most powerful telescopes. Some theories suggest these stars might have formed differently than anything we see today, born not in delicate nurseries of dust and gas, but in the raw, chaotic aftermath of the Big Bang itself. Without heavy elements to cool the collapsing clouds, they could have grown to staggering sizes, shining with a brilliance we can hardly comprehend. Others speculate that their remnants might still linger in the farthest reaches of space, hidden in the shadows of younger galaxies. Then there's the tantalizing clue of their fingerprints. While we can't see the stars directly, astronomers hunt for traces of their existence in the faint glow of the early universe, a whisper of ultraviolet light imprinted on the cosmic background. Some even believe that the mysterious dark matter halos surrounding early galaxies might hold the key, acting as cosmic breadcrumbs leading us back to these primordial giants. So why does any of this matter? Because these stars weren't just the first, they were the architects of everything that followed. Without them, the universe would still be a cold, empty void. Yet, for all their importance, they remain one of astronomy's greatest ghost stories, flickering just beyond the edge of our vision. The search for them isn't just about solving a scientific puzzle, it's about uncovering our own origins, one distant spark at a time. If dark matter truly makes up 85% of the universe's mass, then where is its fingerprint in the cosmic dawn? This is the glaring contradiction that has scientists rethinking everything. According to our best models, dark matter's gravitational pull should have left an unmistakable mark on the early universe, clumping hydrogen gas, accelerating star formation, and imprinting specific patterns on the primordial light we observe today. But when astronomers train their instruments on that ancient era, the signal they expected simply isn't there. One leading theory suggests dark matter might behave differently than we thought. Most experiments assume it's cold, slow-moving and heavy, like invisible boulders scattered through space. But what if it's warmer, faster, or even interacts with itself in ways we haven't accounted for? Simulations show that tweaking these properties could erase the expected signatures, leaving behind a universe that looks eerily smooth in its infancy. Then there's the radical idea that dark matter might not be a single substance at all. Some physicists propose a mix of particles, some heavy and some impossibly light, cancelling each other's effects in ways we're only beginning to model. The hunt for answers isn't just theoretical. Teams are scouring data from radio telescopes like the Murchison Wide Field Array, listening for distortions in the cosmic microwave background that might reveal dark matter's hidden hand. Others are pushing supercomputers to their limits, simulating universes with alternative dark matter rules to see which versions match our observations. And then there's the James Webb Space Telescope, peering deeper into the past than ever before, hunting for whispered clues in the arrangement of the earliest galaxies. What makes this mystery so urgent is its ripple effect. If dark matter played a smaller role in the cosmic dawn than we assumed, it could mean gravity itself worked differently back then, or that some unknown force was shaping the universe. Either scenario would rewrite the textbooks. For now, all we know is that the cosmos is holding its secrets close, and every failed detection only deepens the intrigue. The missing signal isn't just a gap in our knowledge, it's a beacon pointing toward discoveries that could redefine reality as we know it. The cosmic rulebook was supposed to be simple: galaxies take time to grow. Billions of years of slow, steady evolution, gathering gas, birthing stars, gradually brightening like embers catching flame. But the universe loves breaking its own rules. When astronomers pointed the James Webb Space Telescope at targets from the cosmic dawn era, they gasped. There, shining with impossible brilliance, were galaxies so massive, so mature, they had no business existing at such an early cosmic hour. Some of these structures appear fully formed when the universe was less than 5% of its current age, glowing with the light of 100 billion suns packed into tight, dazzling disks. How could such behemoths assemble so quickly? Current models of galaxy formation crumble under the weight of this mystery. Under normal conditions, gravity needs eons to pull together enough gas and dust to build something this colossal. One leading theory suggests these early galaxies might have feasted on streams of cold gas flowing in from the cosmic web, a sort of intergalactic fast food delivery system that fueled runaway star formation. Others propose that supermassive black holes at their cores generated unimaginable energy, lighting them up like cosmic lighthouses far brighter than their modern counterparts. Then there's the unsettling possibility that we're misreading the clues. Could distortions in space-time, lensing effects from invisible matter, or even quirks in how ancient light redshifts be tricking us into seeing ordinary galaxies as impossibly bright? Teams are racing to cross-examine these observations, hunting for subtle signatures that might reveal the truth. But with every new Webb image, the anomaly only deepens. Some of these galaxies appear not just bright but too pristine, lacking the chemical complexity expected after generations of stellar life and death. The implications are staggering. If the laws of physics allowed galaxies to form this rapidly, we might need to rewrite our understanding of dark matter's role or reconsider how quickly stars could ignite in the early universe's unique conditions. Or perhaps, and this is where it gets thrilling, we're glimpsing an entirely unknown chapter of cosmic history, one where the rules were different and the universe worked in ways we've scarcely begun to imagine. For now, these radiant enigmas stand as defiant outliers, challenging us to question not just how galaxies grow, but how well we truly understand the dawn of everything. Imagine a universe so dense and foggy, even light couldn't travel far without bumping into something. That's how things were just a few 100 million years after the Big Bang, a murky sea of neutral hydrogen atoms soaking up every photon, trapping the cosmos in darkness. But then, something extraordinary happened. The fog lifted, the universe became transparent. This monumental shift, known as reionization, is one of the most pivotal yet perplexing events in cosmic history. And here's the kicker, we're still not entirely sure what caused it. For decades, astronomers assumed the culprits were quasars, supermassive black holes at the hearts of young galaxies, blasting out torrents of ultraviolet radiation. These cosmic blowtorches could have ionized the hydrogen, stripping electrons from atoms and clearing the fog like sunlight burning off morning mist. But there's a problem. Recent observations suggest there simply weren't enough quasars in the early universe to do the job alone. The timeline doesn't add up. That's where galaxies enter the picture. The first generations of stars, especially those massive population 3 giants, might have flooded space with enough UV light to kickstart reionization. Simulations show that if even a fraction of these stars formed in dense clusters, their combined radiation could have punched holes in the hydrogen fog, gradually creating bubbles of transparency that eventually merged. But this theory has its own holes. Some of the earliest galaxies we've spotted seem too faint, too small, to account for the scale of reionization. Then there's the wild card, decaying dark matter. A fringe but fascinating idea suggests certain exotic particles might have decayed in the early universe, releasing bursts of energy that could have ionized hydrogen. It's a long shot, but if proven, it would rewrite our understanding of both dark matter and cosmic dawn. The hunt for answers is heating up. Astronomers are combing through data from the James Webb Space Telescope, searching for telltale signs of ionized helium in the most distant galaxies, a smoking gun that would point to the dominant source of reionizing radiation. Others are mapping the large-scale structure of the universe, looking for patterns in how the fog lifted. Was it a slow, sputtering process, or did it happen in rapid, violent bursts? What makes this mystery so gripping is its sheer scale. Reionization didn't just change the universe, it made our existence possible. Without it, light would still be trapped, galaxies would remain hidden, and we'd never see the stars. Yet despite its importance, the forces behind this cosmic curtain call remain shrouded in uncertainty. Every new discovery peels back another layer, revealing a story far more complex and far more thrilling than we ever imagined. Deep in the heart of ancient galaxies, monsters lurk, supermassive black holes so colossal they defy logic. What's truly baffling isn't just their size, but their age. These cosmic behemoths, some weighing billions of times the mass of our Sun, appeared shockingly early in the universe's history, fully formed when the cosmos was barely a toddler. The numbers don't add up. Under normal conditions, even the greediest black hole would need billions of years to feast on enough matter to reach such staggering sizes. Yet here they are, existing when the universe was less than 1 billion years old. How did they grow so fast? One leading theory points to seed black holes, primordial giants born not from collapsing stars, but from the direct collapse of vast clouds of primordial gas. Picture this, in the dense, chaotic soup of the early universe, patches of hydrogen could have collapsed under their own gravity so violently. They skipped the star stage entirely and formed black holes hundreds of thousands of times more massive than any stellar remnant. These seeds would have had a head start, gorging on surrounding gas and merging with one another at breakneck speed, but even this idea strains credibility. Simulations show these seeds would still need near-perfect conditions to grow so rapidly, constant feasting without interruption, like a cosmic buffet with no closing time. Then there's the curveball. What if black holes didn't grow purely by eating? Some physicists speculate that exotic phenomena, like primordial density fluctuations from the Big Bang itself, might have warped space-time in ways that funneled absurd amounts of matter into black holes almost instantly. Others wonder if dark matter played a role, somehow accelerating their growth through interactions we haven't yet imagined. And let's not forget the most radical proposal, that some of these early black holes weren't born from matter at all, but were relics of the universe's violent birth, left behind like scars from the Big Bang. The evidence is maddeningly elusive. Astronomers scour the skies for quasars, the blazing signatures of supermassive black holes devouring matter, hoping their light holds clues. But the earliest quasars we've found are already too mature, their growth spurts seemingly behind them. To crack this mystery, we'd need to catch a black hole in its infancy, mid-feast, a task even the James Webb Space Telescope struggles with. What makes this puzzle so urgent is what it reveals about the universe's rulebook. If black holes can cheat physics to grow this quickly, it hints at gaps in our understanding of gravity, time, or even the fabric of space-time itself. Every new observation tightens the knot, leaving us to wonder, were the early cosmos playing by different rules, or are we just missing a fundamental piece of the puzzle? One thing's certain: the silence of these ancient giants isn't just a mystery. It's a challenge, daring us to rethink everything we know about how the universe builds its most monstrous creations. Somewhere in the faint static between galaxies lies a whisper that could rewrite physics textbooks or vanish into scientific controversy. In 2018, a team of astronomers made headlines with an astonishing claim. They detected the faint echo of hydrogen from the cosmic dawn era, imprinted as a peculiar dip in radio waves at the 21-centimeter wavelength. This signal, they argued, was the fingerprint of the universe's first stars interacting with primordial hydrogen gas. But what made it earth-shattering wasn't just the discovery, it was the signal's depth. The dip was twice as steep as any prediction, suggesting the early universe was far colder than anyone imagined. The implications sent shockwaves through cosmology. If confirmed, it could mean dark matter was cooling hydrogen in ways we've never accounted for, or that some exotic particle was at work, sapping energy from the gas. Theorists scrambled to explain it, proposing everything from interactions between dark matter and hydrogen to undiscovered quantum effects lingering from the Big Bang. For a brief moment, it felt like we were on the brink of a revolution. Then came the twist. Other teams pointed their telescopes at the same patch of sky and heard nothing. No anomalous dip, no hint of ultra-cold hydrogen. The original detection, some argued, might have been drowned out by unaccounted-for radio interference, perhaps even from Earth's own atmosphere. Skeptics noted the signal's frequency overlapped with FM radio bands, raising the specter of mundane human noise masquerading as cosmic revelation. Yet the mystery only deepens. Newer analyses suggest the truth might lie in the subtleties. Could the signal be real but smeared across frequencies we're still learning to untangle? Or is the universe playing tricks, hiding its secrets in the noise itself? The debate has become a high-stakes detective story, with teams refining their instruments to hunt for the faintest whispers in the radio silence. What's at stake isn't just one signal, it's our understanding of the cosmic dawn's very fabric. If the anomaly is real, it implies a universe far stranger than our models predicted. If it's an illusion, it exposes how fragile our grasp of the early cosmos remains. Either way, the hunt continues, a reminder that sometimes the most profound discoveries begin with a flicker in the static, and the courage to ask if we're really alone in hearing it. There's an invisible skeleton stretching across the cosmos, a vast, intricate network of gas and galaxies called the cosmic web. Picture it like the universe's nervous system, glowing filaments millions of light-years long, connecting dense galaxy clusters at their intersections with enormous voids yawning between them. This structure didn't emerge randomly. It's the direct result of gravity sculpting matter over billions of years, except for one glaring inconsistency. When we look back to the cosmic dawn era, this web appears suspiciously well developed, as if the universe cheated on its homework. Here's what baffles scientists. Modern supercomputer simulations running the known laws of physics struggle to recreate the cosmic web's complexity at such early times. They predict a fuzzier, more chaotic arrangement, not the razor-thin filaments and stark voids we actually observe. Somewhere in this mismatch lies a fundamental gap in our understanding. Could dark matter be clumping differently than we've modeled? Maybe its particles interact in ways we haven't accounted for, creating sharper gravitational troughs that funnel ordinary matter into these thread-like structures sooner than expected. Or perhaps the cosmic web didn't form from the bottom up as we assume. Alternative theories suggest that primordial sound waves from the Big Bang, frozen into the universe's fabric as density variations, might have acted like cosmic blueprints, predetermining where filaments would later condense. If true, this would mean the web's seeds were planted in the universe's first nanoseconds, long before stars or galaxies existed. The problem: while this explains the web's regularity, it doesn't fully account for why some filaments appear denser and more pronounced than others so early on. Then there's the wild card, magnetic fields. We often think of them as local phenomena wrapped around stars or galaxies. But new research hints that weak, large-scale magnetic fields might have pervaded the early universe, subtly guiding ionized gas along invisible lines like iron filings on a sheet of paper. If verified, this could explain how thin streams of gas manage to align over cosmic distances without immediately collapsing into blobs. The stakes couldn't be higher. The cosmic web isn't just decoration, it's the delivery system for star-forming fuel, the highway along which galaxies grow. Its structure influences everything from black hole formation to the distribution of dark matter. Yet with every new observation, especially those from the James Webb Space Telescope revealing galaxies perfectly aligned along filaments at record-breaking distances, the puzzle only deepens. What we're witnessing might be more than a scientific challenge. It could be the universe hinting that the rules we've written are incomplete. Perhaps gravity isn't the sole architect. Maybe unknown forces were at work in those first epochs, weaving patterns we're only beginning to trace. Until we solve this, the cosmic web remains both a map and a riddle, its threads glowing with secrets from the dawn of time. Where are all the little guys? If our models of the early universe are correct, the cosmic dawn should be teeming with countless dwarf galaxies, tiny, faint collections of stars no bigger than 1,000th of our Milky Way. These miniature cosmic building blocks were supposed to be everywhere, the leftover crumbs from galaxy formation. But when astronomers scan the skies, they find something startling: a ghost town. The dwarfs are missing, and their absence isn't just a curiosity, it's a full-blown crisis for our understanding of how structure formed in the early cosmos. So where did they go? One possibility is that we're not seeing them because they're too dim. These ancient dwarfs would have been made almost entirely of hydrogen and helium, with very few heavy elements to form dust or bright stars. Their light might be so feeble it's drowned out by the glare of younger, closer galaxies, but even accounting for that, the numbers still don't add up. Telescopes like Hubble and Webb have pushed detection limits to the edge, and the dwarfs remain stubbornly absent. This is where dark matter enters the picture. Dwarf galaxies are thought to form inside small clumps of dark matter, like fireflies trapped in invisible jars. If those clumps behaved differently in the early universe, perhaps because dark matter particles were warmer, faster moving, or interacted with each other, they might not have been able to hold onto enough gas to ignite stars. Simulations suggest that if dark matter was even slightly fuzzier than we assume, it could smooth out the smallest density fluctuations, preventing dwarf galaxies from coalescing in the first place. But there's another twist: feedback. The first generation of stars didn't just shine, they exploded, flooding space with radiation and powerful stellar winds. This cosmic fallout could have sterilized nearby gas clouds, blowing them clean out of their dwarf galaxy hosts before they had a chance to form stars. It's like a primordial hurricane sweeping away the seeds of future galaxies before they could sprout. Some theories even suggest that supermassive black holes in early galaxies unleashed torrents of energy, heating the surrounding intergalactic medium so intensely that smaller galaxies were starved of the cold gas they needed to survive. The stakes are high. If mini-galaxies really are missing, not just hiding, it challenges the very foundation of our bottom-up model of cosmic structure. Maybe small structures didn't merge to form big ones. Maybe the universe skipped a step. Or maybe, just maybe, the laws governing dark matter and star formation were fundamentally different back then. Every new deep field image from Webb brings us closer to an answer, revealing either whispers of these elusive dwarfs or deepening the mystery of why they never existed at all. One thing's clear: their absence isn't just a gap in our maps. It's a glaring question mark hovering over our entire cosmic origin story. Take a deep breath, because the air you just inhaled contains a trace of lithium, an element forged in the furnace of the Big Bang. In theory, that same lithium should be scattered across the universe in predictable amounts, a relic of the first 20 minutes of cosmic existence. Yet when astronomers peer into the oldest stars, those pristine time capsules from the cosmic dawn, they find a glaring discrepancy. The lithium levels are 3 times lower than they should be. This isn't just a minor accounting error. It's a fundamental mismatch that threatens to upend our understanding of the universe's first moments. The mystery begins with Big Bang nucleosynthesis, the process that cooked up the universe's first atomic ingredients. Based on meticulous calculations, physicists predicted exactly how much lithium-7, a specific isotope, should have been produced alongside hydrogen and helium. The numbers were precise, elegant, and seemingly unshakable. But when astronomers turned their spectroscopes toward ancient stars in the Milky Way's halo, relics nearly as old as the universe itself, they found a shocking deficit. These stars, which formed from nearly pure Big Bang material, showed lithium levels that flatly contradicted the predictions. It's as if someone stole a third of the universe's lithium. So where did it go? One camp argues the problem lies in our understanding of stellar physics. Maybe these ancient stars aren't the pristine vaults we assume. Deep in their cores, nuclear reactions or turbulent mixing could have slowly destroyed lithium over billions of years, diluting the original signature. Some simulations suggest that if stars rotate fast enough, their internal winds might dredge up lithium from the core and expose it to blistering temperatures where it fuses into heavier elements. Others propose that lithium gets locked away in stellar atmospheres, sinking out of sight beneath layers of helium-like cosmic sediment. But there's a more radical possibility: the Big Bang didn't produce as much lithium as we think. What if unknown particles, like hypothetical actions or other dark matter candidates, interfered with nucleosynthesis, subtly altering the nuclear reactions in those first explosive minutes? Or perhaps the early universe's expansion rate wasn't as uniform as we've modeled, creating pockets where lithium formation was suppressed. These ideas flirt with heresy, challenging bedrock principles of cosmology. The stakes couldn't be higher. Lithium isn't just some cosmic accessory. It's a benchmark, a litmus test for whether we truly understand the universe's birth. If the deficit stems from stellar processes, it means we've misread the chemical evolution of stars. If it points to gaps in Big Bang physics, we might need to rewrite the opening chapter of everything. For now, the mystery lingers, a quiet enigma written in the light of the oldest stars. Every new observation, every refined simulation brings us closer to an answer, or deeper into the labyrinth. One thing's certain, the universe's lithium ledger is still missing entries, and until we find them, our story of cosmic beginnings remains tantalizingly incomplete. Magnetic fields are everywhere, woven through galaxies, tangled around stars, even threading through the vast emptiness between cosmic structures. But here's the puzzle: no one knows how they got there. These invisible force lines shouldn't exist in the early universe, at least not according to conventional physics. You need moving electric charges to create magnetism, and before stars ignited, the cosmos was just a neutral sea of hydrogen and helium. No currents, no dynamos, no obvious source for the fields we see today. Yet somehow, by the time the first galaxies flickered to life, magnetism had already taken root. The leading theory points to quantum fluctuations in the primordial plasma, those tiny, violent ripples born in the Big Bang's aftermath. Under just the right conditions, these subatomic jitters could have generated weak seed fields, faint as a whisper, weaker than a refrigerator magnet by a factor of 1 trillion. But over billions of years, as gas collapsed into galaxies and stars, these feeble threads might have been stretched, twisted, and amplified by cosmic turbulence, like a microscopic ripple growing into a tidal wave. Simulations show that once started, magnetic fields can self-reinforce, with rotating galaxies acting as colossal dynamos that boost their strength exponentially. But there's a catch. This process takes time, far more time than the universe had before we see fully fledged magnetic fields in early galaxies. That's where alternative ideas come in. Some physicists suggest cosmic inflation, the universe's explosive growth spurt in its first fraction of a second, could have imprinted magnetic fields directly into spacetime itself. Others speculate that phase transitions in the early cosmos, moments when the fundamental forces split apart, might have unleashed bursts of electromagnetic energy, leaving behind lingering magnetic fossils. Then there's the most radical proposal, that dark matter or dark energy, whatever they truly are, might have played a role in magnetizing the cosmos through interactions we don't yet understand. The evidence is frustratingly indirect. Astronomers hunt for clues in the polarized light of distant quasars, whose rays twist as they pass through magnetized intergalactic space. They study the synchrotron glow of galaxy clusters, where charged particles spiral along magnetic field lines like cosmic roller coasters. Even the cosmic microwave background, the afterglow of the Big Bang, might hide subtle hints in the way its light polarizes. But so far, no smoking gun. What makes this mystery so tantalizing is its reach. Magnetic fields shape how gas cools, how stars form, even how black holes feed. Without them, the universe would look profoundly different, yet their origins remain as elusive as dark matter itself. A reminder that even the most pervasive forces in the cosmos can hide their beginnings behind veils of time and physics we're only beginning to lift. Fast radio bursts are among the most head-scratching phenomena in modern astronomy, blisteringly intense pulses of radio waves that flare for mere milliseconds, often never to repeat. But what if these cosmic flashes aren't just random accidents? What if some of them are echoes from the cosmic dawn, carrying secrets from the universe's first chapters? The idea isn't as far-fetched as it sounds. Consider what produces an FRB. Most theories point to extreme objects like magnetars, neutron stars with magnetic fields so strong they could strip atoms apart from half a galaxy away. But here's the twist: magnetars are the corpses of massive stars, and the first generation of stars, those population Roman 3 giants, would have left behind particularly exotic remnants. If one of these primordial beasts collapsed into a magnetar, its death throes might have unleashed FRBs unlike anything we see today. Imagine a magnetic field 1,000 times stronger than modern magnetars, twisting and snapping like a cosmic rubber band, releasing bursts of energy so powerful they've been traveling through space for 13 billion years, only to wash over our telescopes as faint millisecond blips. Then there's the black hole angle. Some FRBs show bizarre patterns, repeating at intervals that defy simple explanations. Could these be the signatures of primordial black holes, those hypothetical leftovers from the Big Bang that might have littered the early universe? If one of these ancient black holes passed through a dense cloud of gas during the cosmic dawn, the violent interaction could have triggered a shockwave, rippling outward as a burst of radio waves. Even stranger, if dark matter consists of primordial black holes, these FRBs might be the only way we'd ever detect them. But the most tantalizing clue lies in the dispersion of FRB signals. As these pulses travel through space, they interact with electrons, scattering slightly like light through a prism. By measuring this scatter, astronomers can estimate how much material the burst passed through, and some FRBs seem to have plowed through far more gas than expected, as if they originated in an era when the universe was denser, murkier. That's exactly what the cosmic dawn was like, a fog of hydrogen so thick it would have left a distinct fingerprint on any radio waves trying to escape. Of course, skeptics argue that linking FRBs to the cosmic dawn is a stretch. After all, we've traced some bursts to relatively nearby galaxies, proving they can happen in the modern universe. But the key word is some. The ones that resist localization, those lone, unexplained flashes from the depths of space, might be the real relics, with new telescopes like the Square Kilometre Array coming online, capable of catching hundreds more FRBs and pinpointing their origins with unprecedented precision. We might finally get an answer. Whether these bursts are cosmic breadcrumbs leading us back to the first stars, or just another dazzling mystery, one thing's clear: the universe loves to surprise us. And if even a handful of FRBs turn out to be whispers from the cosmic dawn, they'd rewrite not just the story of these enigmatic flashes, but our entire understanding of how the universe woke up. Today's universe has rules. Stars aren't supposed to grow larger than about 300 times the mass of our Sun, but the cosmic dawn didn't play by those rules. Scattered throughout the earliest galaxies are chemical signatures hinting at something extraordinary. Stars that dwarfed anything we see now, monsters 500, even 1,000 times more massive than our Sun. These weren't just stars, they were cosmic titans, burning with such ferocity that they could have outshone entire modern galaxies. And their existence throws astrophysics into chaos because, according to everything we know about star formation, they shouldn't have been possible. So how did they defy the odds? The secret lies in the pristine environment of the early universe. Back then, there were no heavy elements, no carbon, no oxygen, none of the complex molecules that help today's gas clouds cool and fragment into smaller stars. Without these ingredients, collapsing clouds of hydrogen and helium couldn't efficiently break apart. Instead, they kept growing, slurping up surrounding material in a runaway feeding frenzy until they reached staggering sizes. Picture a snowball rolling downhill, but instead of stopping at the bottom, it just keeps accumulating mass until it's the size of a mountain. But here's where it gets even stranger. These supermassive stars wouldn't have lived long, maybe just a couple million years, before exploding in spectacular hypernova. Blasts so powerful they'd make modern supernova look like firecrackers. The aftermath of these detonations would have scattered heavy elements across vast distances, seeding the cosmos with the building blocks for future stars, planets, and even life. Some astronomers believe that without these primordial giants, the universe might have remained a sterile wasteland, devoid of the chemical diversity needed for complexity. Yet the evidence for them is frustratingly indirect. We can't see these stars directly. Their light vanished billions of years ago. Instead, we hunt for their ghosts in the chemical compositions of the universe's oldest surviving stars. Certain patterns of elements, like an overabundance of zinc or odd ratios of carbon to iron, act as cosmic breadcrumbs, pointing back to the nucleosynthetic furnaces of these long-dead behemoths. Some ancient stars even contain elements that can only be forged in the heart of a supermassive star's violent death throes. but the mystery deepens when we consider their role in shaping cosmic evolution. If these giants really existed, their radiation would have been so intense, it might have reionized the universe single-handedly, stripping electrons from atoms and ending the cosmic dark ages far earlier than our models predict. Their black hole remnants could have served as the seeds for the supermassive black holes we find at the centers of galaxies today, solving the puzzle of how those objects grew so big so fast. The question isn't just whether these stars existed, it's how many there were, and how they sculpted the cosmos before vanishing without a trace. Every new observation of distant quasars, every simulation of primordial star formation brings us closer to an answer. And if confirmed, these celestial giants wouldn't just be a footnote in cosmic history. They'd be the architects of everything that followed, the towering figures whose brief, brilliant lives set the stage for the universe we know. Imagine a star that defies every law of nuclear physics, one that burns not with hydrogen or helium, but with something far more exotic, dark matter. These hypothetical beasts, known as dark stars, could rewrite the story of the cosmic dawn. Unlike ordinary stars, which shine by fusing atoms in their cores, dark stars would draw energy from the annihilation of dark matter particles colliding inside them, glowing with an eerie, otherworldly light. And if they existed, we might be on the verge of finally spotting them. The idea hinges on a radical twist. In the early universe, vast clouds of hydrogen would have collapsed under gravity, just like in normal star formation. But if those clouds also contained dense clumps of dark matter, the particles could have annihilated upon contact, releasing bursts of energy that kept the gas from fully condensing. Instead of igniting nuclear fusion, the protostar would swell into a colossal, puffy behemoth, up to 10 million times wider than our Sun, radiating a cold, steady glow powered entirely by dark matter's invisible fire. Here's the catch: dark stars wouldn't look like anything in today's sky. Their surfaces would be far cooler than normal stars, emitting mostly infrared light. Their sheer size would make them incredibly faint despite their staggering mass, like cosmic ghosts hovering at the edge of detectability, yet their fingerprints might still linger in the data. The James Webb Space Telescope, with its unparalleled infrared sensitivity, could be the perfect tool to hunt for these anomalies. By scanning the cosmic dawn for objects that are too large, too cool, or too dim to fit standard star models, astronomers might finally catch a glimpse of dark stars or rule them out entirely. Critics argue the case isn't airtight. For dark stars to form, the early universe would have needed just the right concentration of dark matter, enough to fuel annihilation, but not so much that it overpowered normal star formation. Some simulations suggest these conditions were vanishingly rare. Others counter that dark matter's behavior might have been radically different back then, clustering in ways we can't yet predict. And if dark stars did exist, their deaths could have been even stranger than their lives. Instead of exploding, they might have quietly collapsed into black holes, seeding the universe's first supermassive monsters. The hunt is already underway. Teams are scouring Webb's deep field images for objects that match the predicted profile: massive, diffuse, and glowing in the wrong part of the spectrum. A single confirmed detection would revolutionize particle physics and cosmology in one stroke, proving not just that dark matter exists, but that it can shape the cosmos in ways we've barely dared to dream. Until then, dark stars remain one of the most tantalizing what-ifs in science, a reminder that the universe's first light might have been stranger and darker than we ever imagined. Black holes seem to come in two extremes: tiny stellar remnants and supermassive behemoths. But where's the middle ground? Somewhere between a few dozen and a few 100,000 times the mass of our Sun, there should be a whole class of black holes bridging the gap, intermediate mass monsters, the missing link in cosmic evolution. Yet when we scour the cosmic dawn, these mid-sized titans are nowhere to be found. Their absence isn't just odd, it's a gaping hole in our understanding of how the universe builds its most extreme objects. Think of it like a staircase with half the steps missing. We see small black holes formed from collapsing stars, maybe 20 or 30 solar masses. We see supermassive black holes weighing millions or billions of suns squatting in galactic centers, but the steps between them almost entirely blank. Without these intermediates, it's like trying to explain how a sapling becomes a 1,000-year-old redwood overnight, something skipping steps, and that something might rewrite the rules of black hole growth. One theory suggests these middleweight black holes did exist but were swallowed too quickly. In the chaotic environments of early galaxies, where gas was plentiful and mergers constant, 100 solar mass black hole could have gorged itself into supermassive territory surprisingly fast. Picture a cosmic Pac-Man gobbling up everything in its path before we ever got a chance to spot it at an intermediate stage. Simulations show that with enough dense gas funneling into a galaxy's core, even modest black holes can balloon exponentially in just a few 100 million years, a blink in cosmic time. But there's a flaw in this logic. Not every galaxy had these perfect feeding conditions. Some should have hosted black holes growing at slower rates, leaving behind a trail of intermediates. Yet surveys of the cosmic dawn, especially those peering into dwarf galaxies, where growth should have been more leisurely, keep coming up empty. That's led to a wilder idea. Maybe the first intermediate mass black holes formed not from stars but from direct collapses of primordial gas clouds. In the dense, molecule-free environment of the early universe, gas might have collapsed so violently it skipped the star stage entirely, birthing black holes thousands of times heavier than any stellar remnant. The plot thickens when we consider their hiding places. Some theorists argue these black holes weren't at galactic centers at all, but lurking in the outskirts, ejected by gravitational kicks during mergers or galaxy collisions. Others propose they're buried in thick cocoons of dust, their faint X-ray glow smothered by debris. There's even a chance we've been looking for the wrong clues. Unlike supermassive black holes, which announce themselves with blazing quasars, intermediates might reveal their presence through subtler signatures, ripples in star clusters, or the way they subtly warp the orbits of nearby stars. The stakes are higher than just filling a cosmic census gap. If intermediate mass black holes truly are this rare, it suggests supermassive black holes found another, faster path to bigness, one we haven't imagined yet. Or worse, it hints that our understanding of gravity itself might need tweaking in the extreme environments of the early universe. Every new deep field image, every gravitational wave detection brings us closer to an answer. Until then, these missing monsters stand as silent reminders. The cosmos still holds its cards close, and the steps to unimaginable scale might be hiding in plain sight. Tucked away in the farthest reaches of the cosmos float cosmic time capsules, vast, swirling clouds of gas that appear untouched by time itself. These primordial gas clouds, composed almost entirely of hydrogen and helium, seem to have escaped the star-making frenzy that transformed the rest of the universe. Their existence is a paradox. If the cosmic dawn was marked by the birth of stars, why did these clouds remain silent, their gas never igniting into stellar fire? The discovery of these relics sends shockwaves through astronomy. Unlike most gas clouds we observe, which are laced with heavier elements forged in stellar furnaces, these pockets of gas show no traces of carbon, oxygen, or iron, just the pristine ingredients of the Big Bang. It's like stumbling upon a sealed vault from the universe's first moments, its contents perfectly preserved. The most famous example, the Smith Cloud, a massive hydrogen structure drifting near our galaxy, so chemically pure it defies explanation. But the real enigmas lie even farther out, in the distant voids between galaxies, where similar clouds float like ghosts of an earlier era. So why didn't they form stars? One possibility is that they've been hiding in plain sight, existing in regions so isolated, so devoid of the gravitational nudges needed to trigger collapse, that they've lingered unchanged for billions of years. Picture a lone ice cube left in a warm room. Without disturbance, it might take ages to melt. In the same way, without a nearby galaxy's pull or a shockwave from a supernova, these gas clouds could have simply drifted untouched. But there's a thornier explanation. Maybe star formation isn't as inevitable as we think. Some models suggest that under certain conditions, hydrogen gas can resist collapsing into stars even when it's dense enough to ignite. Magnetic fields might play a role, weaving invisible barriers that stabilize the gas against fragmentation. Or perhaps the absence of heavy elements which normally help gas cool and clump kept these clouds too warm and turbulent to settle into stellar nurseries. The debate takes a stranger turn when we consider dark matter's role. If these clouds are nestled within faint, dark matter-dominated mini-halos, their gravity might be too feeble to pull the gas inward efficiently. In this scenario, the clouds aren't entirely primordial, they're failed galaxies, their star-making potential forever stunted by their own invisible scaffolding. Yet the most tantalizing question remains, could some of these clouds truly be pristine, or are we just missing subtle signs of past star formation? Even a single generation of stars would leave traces, faint chemical enrichment, or ripples in the gas from long-dead supernova. Teams using telescopes like the Very Large Array are hunting for these clues, scanning the clouds for whispers of heavy elements or distorted structures. Meanwhile, simulations race to recreate the exact conditions that could lock gas in a perpetual state of near ignition. What's at stake isn't just a cosmic curiosity, it's a window into the universe's default state. If these clouds are truly untouched, they're living snapshots of the raw materials that birthed the first stars. If they're hiding a more complex history, they challenge our assumptions about how and why gas lights up the cosmos. Either way, their silence speaks volumes, a reminder that even in a universe ablaze with stars, some pockets choose to stay forever dark. The universe's first galaxies weren't supposed to have metals, at least that's what we thought. In astronomy, metal means any element heavier than helium, the stuff forged in stars and scattered by supernova. The earliest galaxies should have been pristine, composed only of hydrogen and helium from the Big Bang. Yet when astronomers analyze light from some of the most distant galaxies, they find something shocking. Faint but unmistakable signatures of oxygen, carbon, even traces of iron. It's like opening a textbook to page 1 and finding footnotes from a chapter that supposedly doesn't exist. This anomaly throws the cosmic dawn timeline into chaos. Heavy elements take time to produce. Stars must form, fuse lighter elements in their cores, then explode or shed their outer layers to enrich the surrounding gas. For galaxies just a few 100 million years after the Big Bang to show metal content implies an entire hidden generation of stars lived, died, and polluted the cosmos before we thought star formation even began. Some researchers call these hypothetical pioneers population zero, stars vanishingly rare, unimaginably ancient, and invisible to our telescopes. But how could stars have formed before the cosmic dawn? One radical idea suggests that tiny density fluctuations in the early universe, amplified by dark matter's gravity, might have sparked ultra-early star formation in isolated pockets. These protostars wouldn't have resembled modern ones. Without heavy elements to help gas cool and collapse, they might have been monstrously large and short-lived, collapsing directly into black holes after blazing for mere millennia. Their deaths could have seeded the cosmos with the first heavy elements long before the main wave of star formation began. Then there's the dark horse candidate, exotic stellar objects we've never seen. Some theories propose that quark stars, hypothetical bodies made of ultra-dense quark matter, or even dark matter-powered stars could have existed briefly, their unique physics producing metals through unconventional channels. Others speculate that supermassive stars, hundreds of thousands of times heavier than our Sun, might have fused elements in ways that skipped intermediate steps, spewing out enriched material at unprecedented rates. The evidence keeps getting stranger. Certain ancient galaxies show metal patterns that don't match standard supernova models. The ratios of elements like carbon to oxygen or iron to magnesium suggest nucleosynthesis under extreme conditions, perhaps in the swirling accretion disks of primordial black holes or during violent collisions between neutron stars in the universe's first dense star clusters. Even more puzzling, some early galaxies appear to have uneven metal distributions, with heavy elements concentrated in specific regions like cosmic sprinkles rather than well mixed throughout. This isn't just about rewriting a timeline. If metals existed earlier than predicted, it means the universe's chemical enrichment, the process that eventually built planets and life, started under conditions we've never accounted for. It hints at lost chapters in cosmic history where star formation experimented with rules we've yet to uncover. Every new spectrum from the James Webb Space Telescope deepens the mystery, revealing galaxies that look too evolved, too chemically complex for their age. The cosmos seems to be whispering a secret. Our story began earlier than we dared to imagine, and the clues are written in starlight we're only now learning to read. When quasars blaze across the cosmos, they're supposed to act like cosmic lighthouses, their light cutting cleanly through the intergalactic fog, revealing a predictable pattern of absorption lines as it passes through clouds of hydrogen. But some of the oldest quasars refuse to follow the script. Their light arrives carrying bizarre, unexplained dips and spikes in specific wavelengths, as if something out there in the void is warping their signal in ways physics can't yet explain. These anomalies aren't just technical glitches, they're potential windows into a hidden layer of the early universe, one where the rules of light and matter might have worked differently. Take the case of quasar Euler's-Jones 1142 plus 006. When astronomers analyzed its spectrum, they found a forest of absorption lines where there should have been smooth transitions. The strangest part, the wavelengths of these lines correspond to elements like carbon and silicon, materials that shouldn't have existed in significant quantities so early in cosmic history. It's like finding a modern-day power plant humming away in the Stone Age. One theory suggests these elements might have been forged not by stars, but by something far more exotic: the explosive collisions of primordial black holes or the violent turbulence of the universe's first magnetic fields. Then there's the mystery of uneven ionization. Some quasar spectra show patches where hydrogen appears completely ionized, stripped of electrons, right alongside regions where it's strangely neutral. This patchwork pattern doesn't match any known process of UV radiation from stars or quasars. Could there have been another ionizing source at play? Some researchers point to decaying dark matter particles, which might have released bursts of energy capable of tearing electrons from hydrogen atoms in erratic, localized surges. Others speculate that the intergalactic medium itself was clumpier than we've modeled, with pockets of dense gas acting like cosmic sponges, soaking up ionizing photons before they could spread uniformly. Perhaps the most baffling anomaly comes from quasars whose light seems to have dimmed in transit. One leading explanation invokes gray dust, hypothetical particles unlike anything in the modern universe, floating between galaxies and selectively absorbing certain wavelengths. But here's the twist: this dust would need properties that defy known physics, absorbing light without scattering it, like a ghostly filter tuned to specific colors. Alternative ideas stretch even further. Could spacetime itself have been subtly different during the cosmic dawn, warping light in ways we've never accounted for? Or might the expansion of the universe have accelerated briefly in certain regions, redshifting quasar light unevenly across space? The hunt for answers is rewriting our toolkit. Teams are developing new spectral analysis techniques, teasing apart quasar light with machine learning to spot patterns invisible to the human eye. Others are running ultra-detailed simulations of the early intergalactic medium, testing how turbulence, magnetic fields, or exotic particle interactions might leave fingerprints in ancient light. Every anomalous quasar is a cipher, and the key to decoding it might lie not just in distant galaxies, but in the very fabric of reality itself. What makes these quirks so thrilling is their defiance. They're not just gaps in our knowledge, they're glaring inconsistencies, places where the universe seems to wink at us, hinting that the story we've told about its dawn is missing whole chapters. As we peel back the layers, one spectrum at a time, we're not just solving a puzzle. We're glimpsing the shadow of a younger, wilder cosmos, one that played by rules we're only beginning to uncover. Hidden somewhere in the faint glow of the cosmic microwave background might lie the echoes of the universe's most violent births, the explosive deaths of its very first stars. These weren't ordinary supernovae. When a population 3 star, hundreds of times more massive than our Sun, reached the end of its brief, fiery life, it didn't just fade away. It detonated with such unimaginable force it could outshine entire galaxies, scattering newly forged elements across the cosmos. But here's the puzzle. If these explosions were so colossal, why haven't we found their remnants? The answer might be written in the oldest light we can see, the afterglow of the Big Bang itself. The cosmic microwave background, or CMB, is more than just a snapshot of the infant universe. It's a canvas imprinted with every major event that followed. Tiny fluctuations in its temperature and polarization tell a story of density variations, cosmic expansion, and yes, possibly even the aftermath of those first supernovae. Researchers have long suspected that the energy released by these early explosions could have left subtle ripples in the CMB, like fingerprints pressed into cooling wax. The logic is tantalizing. When a supernova's shockwave plowed through the surrounding hydrogen gas, it would have heated patches of the universe unevenly, creating minute-hot and cold spots that might still linger in the background radiation. But detecting these imprints is like searching for a single whisper in a hurricane. The CMB's patterns are already a complex tapestry, woven by everything from inflation to galaxy formation. Isolating a supernova's signal requires sorting through layers of cosmic noise, distinguishing between the echoes of stellar death and the fingerprints of other primordial processes. Some teams are focusing on specific polarization patterns, twists in the CMB's light that could betray the passage of ancient shockwaves. Others hunt for odd chemical signatures in the oldest stars, like excess zinc or unusual isotope ratios, which might point back to the unique nucleosynthesis of those first explosions. Then there's the wild card, pair instability supernova. These are the ultimate cosmic fireworks, a rare type of detonation that occurs only in the most massive stars. Unlike regular supernova, which leave behind neutron stars or black holes, pair instability blasts vaporize the entire star, leaving no remnant at all, just a burst of energy so powerful it could have briefly reheated portions of the early universe. If these events were common during the cosmic dawn, their ghostly signatures might still be hiding in the CMB's fine-scale fluctuations, waiting for a telescope sensitive enough to tease them out. The hunt isn't just academic. Finding these echoes would do more than confirm the existence of the first stars. It would reveal their lives and deaths in startling detail. The amount of energy they released, the metals they spewed into the void, even the way their explosions shaped the growth of the first galaxies. It's all encrypted in those ancient ripples. And with next-generation telescopes like the Simons Observatory and CMB S4 coming online, we're closer than ever to cracking the code. Yet for all the promise, the search is fraught with uncertainty. What if the first supernova were too few, their signals too faint to rise above the cosmic static? Or worse, what if they've been overwritten by later events, their whispers drowned out by the universe's own growing noise? The answers lie somewhere in that primordial glow, a faint but stubborn reminder that even the most cataclysmic events leave traces, if only we know where to look. Scattered across the early universe like ghostly beacons, vast clouds of hydrogen glow with an eerie ultraviolet light. stretching hundreds of thousands of light-years across, yet with no obvious source of power. Astronomers call them Lyman alpha blobs, and they're among the most baffling structures from the cosmic dawn. These enormous, diffuse halos of energized gas shouldn't exist under normal circumstances. Hydrogen only glows this brightly when it's been blasted by intense radiation, but when we point telescopes at these blobs, we often find nothing. No galaxies, no quasars, no visible engines capable of lighting up such colossal structures. It's as if the universe left the lights on in a room no one's using. One leading theory suggests these blobs are illuminated by galaxies we just can't see, drowned out by their own brilliance. Picture a flashlight submerged in fog. The beam scatters so much you'd see the glow long before spotting the light source itself. In the early universe, young galaxies blazing with star formation might be shrouded in thick cocoons of gas, their visible light smothered while their ultraviolet radiation leaks out, exciting the surrounding hydrogen into that distinctive Lyman alpha glow. The James Webb Space Telescope has started uncovering hints of this, spotting faint galaxy clusters embedded in some blobs that Hubble missed. But even with Webb's vision, many blobs remain stubbornly hostless, their central engines still hidden. Then there's the more exotic possibility. What if the radiation isn't coming from stars at all? Some blobs exhibit energy signatures that don't quite match normal stellar processes. Could they be fueled by supermassive black holes in an early growth spurt, their accretion disks pumping out radiation before they'd fully formed visible quasars? Or perhaps they're the aftermath of monstrous galactic collisions, where shock waves from crashing gas clouds heated hydrogen to glowing temperatures without triggering immediate star formation. Simulations show that in the dense environments of the early universe, such violent encounters might have been common, leaving behind these ephemeral, glowing scars. But the real curveball comes from the blob's sheer size. Some span diameters several times larger than our Milky Way, yet their gas is so thinly spread, it would barely register as a vacuum by Earth standards. How could something so tenuous shine so brightly? One radical idea points to dark matter, not as a passive scaffold, but as an active participant. If certain dark matter particles decayed or collided in the early universe, they might have released bursts of energy that could excite hydrogen on scales we've never seen in modern times. It's a long shot, but if true, these blobs wouldn't just be cosmic oddities, they'd be the first visible evidence of dark matter's hidden interactions. Every new observation adds layers to the mystery. Some blobs appear perfectly spherical, like cosmic soap bubbles. Others twist into intricate filaments, weaving through space like glowing spiderwebs. A rare few even seem to pulse over time, their brightness flickering in ways that defy easy explanation. The only certainty is that they played a crucial role in shaping the early universe. Their radiation would have helped ionize the cosmic fog, carving out transparent bubbles that allowed light to travel freely for the first time. What makes these glowing enigmas so compelling isn't just their origin, it's what they represent. They're the universe's unanswered voicemails, signals from an era when the rules of structure formation were still being written. Whether powered by hidden galaxies, violent collisions, or something even stranger, Lyman alpha blobs remind us that the cosmic dawn wasn't just a time of first light, it was a canvas for phenomena we're only beginning to decipher. And with each discovery, we're not just solving a puzzle. We're learning how to read the universe's own handwriting, scrawled across the sky in ultraviolet ink. The universe keeps meticulous books, or at least it should. According to the most precise calculations, the cosmic dawn era ought to contain a specific amount of normal matter, the stuff we're made of: protons, neutrons, electrons, the baryons. But when astronomers tally up all the visible stars, galaxies, and gas clouds from that ancient epoch, they come up shockingly short. Nearly half the baryons are missing. It's like checking your bank statement only to discover half your savings have vanished without a trace. These aren't exotic dark matter particles or unexplained energy. This is the ordinary material that should form everything we see. So where did it go? One clue lies in the cosmic web's faintest threads. Between galaxies stretch vast, diffuse filaments of gas so hot, they glow not in visible light but in X-rays. This warm, hot intergalactic medium, or WIM, could be hiding the missing baryons in plain sight. The gas here is so thinly spread, a cubic meter might hold just a few atoms, yet across billions of light years it adds up. The problem, detecting this tenuous material, is like trying to spot fog by the light of a single candle. Current telescopes barely glimpse its faint X-ray shimmer, leaving huge gaps in the map. But the plot thickens. Even accounting for the WIM, the numbers still don't quite balance. Some theorists suggest the missing baryons might be masquerading as something else trapped in strange, low-density pockets we've overlooked. Imagine a cosmic magician's trick, matter not gone, just stretched so thin it's invisible to our instruments. Others propose more radical ideas. Could some baryons have been converted into dark matter through interactions we've yet to discover? Or might they be locked away in primordial black holes, tiny relics from the Big Bang itself? Then there's the tantalizing possibility that our observations are simply incomplete. The cosmic dawn's chemistry was drastically different from today's universe. Without heavy elements to act as cooling agents, gas might have behaved in ways that defy modern analogs. Certain simulations show baryons condensing into exotic, ultra-faint structures, dark galaxies with no stars, or sprawling hydrogen halos too cool to emit detectable radiation. The James Webb Space Telescope is hunting for these ghosts, peering into voids where conventional models predict nothing, yet anomalies might lurk. What makes this mystery so urgent is its universality. These missing baryons aren't just a cosmic accounting error, they're the raw material of everything. Their distribution shaped how galaxies formed, how light escaped the early cosmos, even how the first molecules assembled. If half the universe's building blocks are hiding, we might be misunderstanding the most basic rules of structure and growth. The hunt is far from over. New X-ray observatories like the upcoming Athena mission aim to scan the skies with unprecedented sensitivity, while radio telescopes trace the faintest whispers of hydrogen. Every improvement in technology peels back another layer of the cosmic veil. Yet for now, the missing baryons remain a silent majority, their absence a reminder that even the ordinary can become extraordinary when the universe decides to play hide and seek. Black holes aren't supposed to be speed demons, at least not the supermassive ones. Conventional wisdom says these cosmic monsters should spin modestly, their rotation slowed by the chaotic way they gorge on gas and merge with other black holes. But the early universe didn't get the memo. When astronomers measure the spin rates of supermassive black holes from the cosmic dawn, some are whirling at nearly the maximum speed allowed by physics, so fast their event horizons stretch into oblong shapes. This isn't just a curiosity, it's a direct challenge to everything we thought we knew about how these behemoths grew so big so fast. How does a black hole even get spinning this rapidly? Picture a figure skater pulling their arms in to spin faster, but instead of arms, imagine an entire galaxy's worth of gas spiraling inward in a smooth, orderly disk. If a black hole feeds steadily from one direction over millions of years, that consistent torque can rev it up like a cosmic top. The problem, most black holes don't get to eat so neatly. In the messy environments of the early universe, gas should have poured in from all angles, with mergers and collisions sending chaotic streams of matter tumbling into the abyss. That kind of chaotic feeding would have cancelled out any spin, leaving black holes rotating lazily at a fraction of their possible speed. The fact that some are spinning at 90% of light speed suggests they grew under freakishly perfect conditions, like winning the cosmic lottery over and over. Then there's the growth paradox. Fast-spinning black holes are picky eaters. As their rotation approaches the limit, the centrifugal force becomes so strong it flings away incoming gas unless it hits the accretion disk at just the right angle. This makes it harder for them to keep growing, creating a natural speed limit. Yet these early black holes somehow became supermassive while spinning wildly. It's like trying to fill a bathtub with the drain wide open unless something was plugging that drain. Some theorists suspect magnetic fields played bouncer, trapping gas near the event horizon long enough to be swallowed despite the spin. Others propose these black holes skip the messy growth phase entirely, forming already massive and spinning from direct collapse cosmic cheat codes that let them bypass the usual rules. The wildest twist comes from relativity's playbook. At extreme spins, a black hole's ergosphere, the region just outside the event horizon where spacetime itself gets dragged around, becomes a powerhouse. Particles entering this zone can steal rotational energy and escape with boosted velocity, a process called the Penrose mechanism. If these early black holes were spinning fast enough, they might have unleashed torrents of high-energy particles, lighting up their host galaxies in ways we've never seen. That could explain why some of the brightest quasars from this era seem impossibly energetic. Their black holes weren't just eating, they were revving like engines, turning rotation into raw radiation. Yet the mystery deepens when we ask why this rapid spin seems unique to the early universe. Modern supermassive black holes, like Sagittarius, a star at our galaxy's center, spin modestly, if at all. Did cosmic conditions back then favor some perfect alignment of gas flows we've yet to replicate in simulations? Or was there an entirely different mechanism at work, one that's since faded from the universe? Every new measurement of these ancient spins tightens the knot, forcing us to reconsider not just how black holes grow, but how the raw chaos of the cosmic dawn could occasionally produce something so finely tuned. What's at stake isn't just a detail of black hole mechanics. Spin rate affects how black holes launch jets, shape galaxies, and even ripple spacetime with gravitational waves. If the early universe could mass-produce these ultra-fast spinners, it might mean we've underestimated their role in ending the cosmic dark ages, their furious rotation possibly acting as cosmic power grids, channeling energy across galaxies. Or perhaps we're glimpsing a lost chapter of physics, where conditions in the primordial cosmos allowed black holes to break rules that later became ironclad. Either way, these spinning enigmas remind us that even the darkest objects in the universe can hold dazzling surprises. Dust seems like a cosmic afterthought, just flecks of carbon and silicon left behind by dying stars. But in the early universe, dust plays a starring role, and its sudden appearance is rewriting our timeline of cosmic evolution. Here's the puzzle. Dust shouldn't exist in significant quantities until hundreds of millions of years after the first stars, when generations of supernova had time to forge and scatter heavy elements. Yet when astronomers peer back at galaxies from the cosmic dawn, some are already shrouded in thick dust clouds, as if the universe hit fast forward on its dust production cycle. This isn't just a minor discrepancy, it's a full-blown paradox that hints at hidden stellar factories or entirely new physics. Take Galaxy A1689ZD, one of the earliest dusty galaxies ever spotted. It's so choked with dust it appears redder than it should, its starlight dimmed by cosmic soot. The kicker: this galaxy existed when the universe was barely 700 million years old. For it to harbor that much dust, stars must have been churning out heavy elements at a rate dwarfing anything in the modern universe. But how? Normal supernovae take tens of millions of years to enrich their surroundings. Even the most optimistic models can't explain how enough stars could have lived, died, and polluted their galaxies that quickly. One radical solution lies in the nature of those first stars. Population Roman 3 stars, the universe's pioneering giants, might have died in explosions unlike anything we see today. Instead of typical supernova, they could have undergone pair instability events, cataclysmic detonations so powerful they vaporized the entire star, spewing out massive amounts of heavy elements in a single violent pulse. Simulations show these blasts could have produced up to 100 times more dust per star than modern supernova, seeding the cosmos with soot at record speed. The catch: pair instability. Supernova require stars of very specific masses, and it's unclear if enough existed to account for the dust we're seeing. Then there's the dark horse candidate, supermassive stars. A handful of theorists argue that under the unique conditions of the early universe, gas clouds might have collapsed directly into stars weighing millions of solar masses. These unfathomable giants would have burned for only a few 100,000 years before collapsing into black holes, but their sheer scale could have flooded their surroundings with dust in a single lifetime. It's a fringe idea. No one's ever observed such a star, and their formation remains speculative. But if even a few existed, they could explain the dust surplus we're finding. But what if stars aren't the only dust producers? Some researchers point to quasars as potential cosmic factories. The intense radiation and turbulent winds around supermassive black holes might have forged dust grains directly from raw gas, skipping the stellar middleman. Others speculate that cosmic rays, high-energy particles flooding the early universe, could have catalyzed dust formation in ways we don't yet understand. There's even a wild-card possibility that some of this dust isn't dust at all, but strange quantum structures left over from the Big Bang, masquerading as ordinary particles. The implications ripple far beyond astronomy trivia. Dust isn't just cosmic clutter, it's the raw material for planets, the catalyst for molecule formation, and the coolant that allows gas clouds to collapse into new stars. If dust appeared earlier than thought, it means the universe might have been building complex structures faster than we dreamed, accelerating the path to galaxies, planets, and life. Every dusty galaxy we find pushes the timeline back further, forcing us to ask, were the cosmic dawn stars more prolific, more exotic, or were there entirely unknown forces at work, sprinkling the universe with stardust before the recipe was supposed to exist? The hunt for answers is heating up. The James Webb Space Telescope's infrared eyes are perfect for spotting dust's thermal glow, while ALMA radio antennas trace its chemical fingerprints. With each new observation, we're not just solving a cosmic accounting error, we're uncovering a hidden chapter in how the universe built its way from simplicity to complexity, one grain of dust at a time. Every dawn must fade, but how did the universe's first age of light finally give way? The end of the cosmic dawn wasn't just a clockwork transition. It was a cosmic revolution, tearing through the fabric of space and time. For hundreds of millions of years, the universe had been a hazy, half-lit realm, its hydrogen fog slowly burning away under the glow of newborn stars. Then, suddenly, or so it seems, the fog lifted, the light won, and the cosmos as we know it emerged. But how it happened remains one of the most contentious debates in cosmology. Was this a synchronized event, washing over the universe like a tide, or a chaotic mosaic, stitched together by countless local fires? The traditional view paints a clean picture. Radiation from the first galaxies and quasars grew intense enough to strip electrons from hydrogen atoms on a universal scale, like sunlight evaporating morning mist. This process, called reionization, should have unfolded relatively smoothly, with ionized bubbles expanding and merging until the entire cosmos became transparent. Observations of the cosmic microwave background seem to support this. Its polarization patterns hint at a fairly rapid, homogeneous transition ending around redshift 6, when the universe was roughly 1 billion years old. But dig deeper and the cracks appear. New data from the James Webb Space Telescope reveals a messier story. Some pockets of the universe appear to have cleared their hydrogen fog shockingly early, while others held out like stubborn patches of twilight. Distant quasars from this era flicker in and out of view, their light sometimes absorbed by lingering neutral hydrogen clouds long after reionization was supposed to be complete. It's as if the cosmos didn't flip a single light switch. It stumbled through a labyrinth of dimmers, with some regions blazing bright while others lagged behind. This patchwork pattern forces astronomers to reconsider the engines behind reionization. Could local phenomena like clusters of especially massive stars or freakishly active black holes have dominated the process? In denser regions of the early universe, where galaxies crowded together like fireflies in a jar, radiation might have overwhelmed the hydrogen quickly. But in the sparse outskirts, light could have trickled out slowly, leaving isolated islands of darkness for eons. Some simulations even suggest that cosmic filaments, those vast thread-like structures of gas, acted as ionizing highways, channeling radiation along invisible routes while bypassing less connected voids. Then there's the wild card, cosmic variance. We're seeing just one sliver of the universe's history, and it might not be representative. What if our observable corner simply got lucky, with an unusual concentration of early galaxies that skewed the timeline? Or worse, what if reionization wasn't even driven primarily by stars and quasars? Fringe theories propose that dark matter decay or even collisions between primordial black holes could have unleashed ionizing bursts, creating a chaotic, uneven landscape of light and shadow. Yet the most tantalizing clues come from the survivors' galaxies that somehow formed before reionization ended. These cosmic holdouts, like the recently discovered Jade's GC 13-0, thrived in neutral hydrogen, seemingly untouched by the ionizing fury around them. Their existence suggests that the cosmic dawn didn't end with a bang, but with a whimper, its final pockets of resistance fading quietly as the last stars stirred the remaining fog. What's at stake isn't just a timeline, it's the very nature of cosmic evolution. If reionization was a universal tide, it implies a level of coordination in the early universe that borders on miraculous. If it was a patchwork, it means the cosmos fashioned its own transparency piece by piece, with each galaxy or black hole contributing a stroke to the larger canvas. Both scenarios challenge our assumptions, forcing us to ask, was the end of the cosmic dawn a decree from above or a rebellion from below? The answer, much like the dawn itself, might still be emerging from the dark. Beneath the glow of the first stars and the whispers of ancient hydrogen, there's a ghostly sea of particles streaming through the cosmos, neutrinos, born in the universe's fiery first second. These elusive phantoms, nearly massless and almost impossible to catch, carry secrets from the cosmic dawn we've never been able to read. They're the universe's oldest messengers, forged in the Big Bang's aftermath, yet they've slipped through our detectors for decades. But what if we could catch them? What if the faintest whispers of the cosmic neutrino background, the primordial echo of creation itself, still linger, hiding clues about the universe's most violent beginnings? The challenge is almost laughably immense. Neutrinos barely interact with matter. Trillions pass through your body every second without a trace. The cosmic neutrino background is even fainter than the cosmic microwave radiation we've mapped so meticulously. These particles cooled to near absolute zero as the universe expanded, their energy stretched into oblivion over 13 billion years. To detect them, we'd need a telescope sensitive enough to spot a candle flickering on Pluto from Earth. Yet the tantalizing promise keeps physicists awake at night. Locked in those ghostly signals could be answers to questions we've barely dared to ask. Did the infant universe have hidden dimensions? Was there a brief epoch when neutrinos ruled the cosmos? And most hauntingly, what happened in the first fraction of a second before the cosmic dawn even began? Some think the key lies in gravity. Neutrinos, despite their shyness, have mass and mass warp spacetime. In theory, the collective gravitational pull of the cosmic neutrino background might subtly bend the light of distant galaxies, creating distortions we could tease out with next-generation telescopes. Others are hunting for rare neutrino relics that might have been slowed or trapped in the early universe's dense plasma, leaving faint imprints in the distribution of galaxies we see today. There's even a wild hope that certain radioactive decays on Earth could be influenced by these ancient neutrinos, like a whisper nudging a pendulum. But the boldest ideas border on science fiction. Imagine a detector the size of a solar system, using the sun's gravity as a lens to focus these feeble signals, or a network of quantum sensors so precise they could catch the infinitesimal shiver of a neutrino passing through a crystal lattice once in a century. Some theorists speculate that if neutrinos interacted with dark matter in ways we haven't yet imagined, their primordial background might have left scars in the large-scale structure of the cosmos, an invisible ink only readable with the right cosmological cipher. The irony is exquisite. These particles, forged in the universe's hottest moment, now drift through the coldest voids, unchanged since the first tick of time. If we could finally listen to their story, it wouldn't just rewrite the chapter on the cosmic dawn, it would rip open the prologue. The cosmic neutrino background isn't just a signal. It's a time capsule from the universe's very first breath, waiting for us to crack the seal. And if we do, we might find that the dawn we've been chasing was just the second act of a much stranger play. They were the titans of creation, blazing across the young cosmos before vanishing without a trace, or so we thought. The fate of population 3 stars, those first celestial behemoths, might not be as final as we once believed. While their light faded billions of years ago, their remnants could still linger in the darkness, hiding in plain sight. Imagine if some of these ancient giants collapsed not into oblivion, but into cosmic survivors, black holes or neutron stars drifting silently through the modern universe, carrying secrets from the dawn of time. Take black holes first. The most massive population 3 stars wouldn't have gone quietly. Instead of scattering their matter in supernova, some might have imploded directly into black holes hundreds of times heavier than our Sun. Unlike modern stellar black holes, which rarely exceed 50 solar masses, these primordial relics could be the missing link between stellar and supermassive monsters. And here's the twist: they wouldn't have to hide in distant galaxies. Simulations suggest thousands could be lurking right here in the Milky Way's halo, carried inward over eons by the gravity of merging dwarf galaxies. They'd be nearly invisible unless actively feeding, but their presence might betray itself through subtle tugs on nearby stars or the occasional flare as they rip apart a passing comet. Neutron stars offer an even more tantalizing possibility. If some of the first stars weren't quite massive enough to collapse into black holes, they might have left behind ultra-dense neutron stars, but with a twist. Born from pure hydrogen and helium, these exotic remnants could have properties unlike anything we see today. Some theorists speculate they might crystallize into strange quark stars, their cores so compressed that protons and neutrons dissolve into a soup of free quarks. Others suggest their magnetic fields could be orders of magnitude stronger than modern magnetars, fossilized echoes of the early universe's turbulence. Then there's the wild card objects we haven't even imagined. The physics of the cosmic dawn was so extreme, it might have birthed stellar remnants that no longer exist in today's universe. Picture electroweak stars, hypothetical bodies where the crushing pressure triggers exotic particle transformations near the core, or boson stars, composed not of matter but of elusive dark energy particles. These would be nearly undetectable except through their gravitational shadows, but their existence would rewrite the rules of stellar evolution. The hunt for these relics is already underway. Astronomers scan gamma-ray bursts for odd signatures that might betray ancient neutron stars. Gravitational wave detectors listen for the faint chirps of primordial black hole mergers. Even the subtle wobbles of stars in our galaxy's outskirts are scrutinized for signs of invisible, massive companions. Every unusual object, like the bizarre Planet 9, candidate perturbing distant orbits in our solar system, gets a second look. Could it be a wandering black hole from the cosmic dawn? What makes this search so electrifying isn't just the prospect of finding a fossil from the universe's infancy. It's the chance to touch a time when the rules were different. These remnants wouldn't just be dead stars, they'd be time capsules preserving conditions we can't recreate anywhere else. Their very atoms remember an era before planets, before metals, before light itself had fully escaped the cosmic fog. And if they're out there, hiding in the dark, they're waiting to tell us a story, one that begins with the first sunrise of creation. From the ghostly whispers of population, 3 stars, to the baffling absence of intermediate black holes, these 25 mysteries aren't just cosmic curiosities. They're gaping holes in our understanding of reality itself. Each one appends assumptions we once considered unshakable. Why do early galaxies appear impossibly mature? How did supermassive black holes grow so quickly? What erased half the universe's normal matter before we could even map it? These aren't small puzzles, they're seismic tremors beneath the foundations of cosmology, forcing us to question whether we've misunderstood gravity, dark matter, even the very nature of time. The cosmic dawn wasn't just an era, it was a revolution, one we're only now decoding, but the answers may be closer than we think. The James Webb Space Telescope is peeling back layers of time with unprecedented clarity, while upcoming missions like the Square Kilometre Array will listen for radio whispers from the universe's first atoms. The Nancy Grace Roman Space Telescope aims to chart dark matter's shadowy architecture, and gravitational wave detectors like LISA could catch echoes of primordial black holes colliding. On Earth, particle accelerators are recreating conditions from the first trillionth of a second, hunting for exotic particles that might explain dark matter's role in shaping the early cosmos. We stand on the brink of breakthroughs that could rewrite textbooks within a decade. This isn't just science, it's a detective story spanning 13 billion years, and you've got a front row seat. Every new observation, every flicker of data brings us closer to understanding our celestial origins. So tell us, which mystery keeps you up at night? Is it the missing dwarfs, the lithium deficit, or those eerie Lyman alpha blobs glowing with no power source? Drop your thoughts in the comments, and if you're hungry for more cosmic enigmas, hit subscribe. The universe has spent eons hiding its secrets. Together, we're finally bringing them into the light.